Today we're going to talk about functors. So I thought I could give you some kind of explanation based on the mathematics, but maybe it would be easier to just show you an example of the implementation first, and then later or afterwards we can talk about the formalization and what it means in a different context and how to understand these concepts. Maybe it will give you some, just provide you with some context. But without further ado, so let's say we have a class. I'm just going to define a data class called functor. A data class is just allowing me to write value of t right here instead of having to explicitly define an init method, which is a little bit more verbose, but it's more or less equivalent to implementing it directly. And this class functor, it has two methods. It has a unit method. So this method, I call it unit. It's just a very simple basic method that is just equivalent to instantiating an instance of the class. Some people might also call it pure, for example. It can have different names, but what you have to understand for now is that basically this unit is just equivalent to instantiating an instance of the class. So you can either call functor of 1 to create a new instance with this wrapped value of 1, and that is completely equivalent to saying this. You might wonder, why do we define that explicitly when we already have the option of just instantiating an instance? And the reason is that we want this to be a base class that we can inherit from, right? So if we end up having to declare a different functor, so maybe let's call it functor 1, and we want to be able to write something like this. In the case that we are accessing some other methods that are like recursive, right? That are instantiating again instances of the same class, then we want it to be instantiating instances of this child class and not just of the base class, which would be the case if we would write something like this, for example. Okay, so that's the motivation for defining this unit method. So we have our functor with two methods, unit method and fmap method. So what is this method fmap doing? It's taking a function. If you don't know this syntax fn, I recommend you watch my other video on type aliases. So we have a function from t to u, right? Some type t could be an integer, u could be another integer, for example, it could be a string. And this function fmap is going to apply that function to the value, and conveniently, because this is a function from t to u and our value is of type t, this will always be properly typed, and then it's going to return a new instance of a functor, but a functor of type u. Okay, so just instantiate like this, you can see it's a functor with a value of 1. And then if we apply some function with fmap, for example add 1, right? You could also write it like this, which is a little bit more easy sometimes to do it in line, right? You can see that it has applied that function to the wrapped value, right? And one of the things I like to do when I'm writing code like this, which permits this kind of chained operation, is to bind this or to make equivalent to this kind of operator that is responsible for the composition or changing to some kind of left-associative magic method in Python. So there's a bunch of them. When you write 1 plus 1, for example, here, then what is the Python interpreter doing? It's basically going to first compute this, right? Because that is what left-associative means. And then it will compute this, right? So first it will compute that this is 2, and then it will add another one. What's happening under the hood is this 1 is an instance of type int, right? Int, and then this int will have a magic method implemented called add, and that basically takes a self, right? It will take the value of the integer itself, and then it will also do something with another value, right? So you have the self and the other, that are two arguments to this kind of binary magic methods. Okay, so we got this lshift method, and so what do we want to do? We want to use this as an alias for fmap. So let's say it will have the same type signature. It will take some function from t to u, right? So maybe let's declare u again here, u. And then we want this to be a function to functor of u, and so what we're going to return is self.fmap of f. Okay, so what does this allow us to do? We've just replaced this fmap with L-shift. So that means that right now we have a new syntax that we unlocked. So right now we can write expressions like this. And I think this is just so really clean, because now, I mean, look how cool this is. You're basically defining your own syntax in Python by binding this mapping method, or these composition methods, right? That take two arguments, namely the self and the other. Because these operations are chainable, you get this really nice syntax that you unlock, and you know, it's cool to have. So that's it. Just a short recap. We had our unit method to create a new class instance. We defined the fmap, which applied some kind of function to the wrapped value, returning a new wrapped value after the function had been applied. And then, for simplicity's sake, we used this left-associative magic method in Python in order to be able to create this very cool syntax, allowing us to basically chain operations and applying them in a turn to our functorial value. So I hope this gives you some inspiration, and